We've used Ampere's law to discover the magnetic field produced by a current-carrying conductor, and it was mu 0 I over 2 pi r. Now let's extend that to a cylinder of conducting, a cylindrical conductor, with the conduction being uniform throughout. So the current is uniform throughout the volume. So first we'll consider, for the radius less than the radius of the cylinder, what's going on? Well, this region of space is enclosing a certain amount of current. So the B field, as before, as you would expect with your thumb coming out of this cylinder, right hand circles counterclockwise. There's the B field. How big is it? Well, Ampere's law says closed integral of B dot dl is B2 pi r in this case, which is mu 0 I enclosed. So we just need to figure out I enclosed and we're home free. Now current density is current per area, which is current over pi r squared, big R squared of course. So I enclosed is that part of the area that's enclosed by the region of concern here. So it's current density times the area. So there's current density, I over pi r squared times pi r squared. Gives us I r squared over r squared, little over big R. So then the magnetic field is mu 0 I enclosed over 2 pi r, which is mu 0 I little r squared over 2 pi r big R squared. And we have mu 0 I r over 2 pi big R squared. Notice now, instead of being inversely proportional to r, it's proportional to r. It's not inversely, this is a constant, so that's in the denominator. So the bigger r is, and this is really big, well then that kind of like dilutes the current density, and so it makes the B field smaller because you're enclosing less charge proportionally. Then the other thing to do is just consider when r is bigger than the radius of the conductor. So it's this region. Let's do the line integral around that. The B field coming off in the same direction. Now I enclosed is just I, all of it. So we can just write it down. Mu 0 I over 2 pi r. It looks just like an infinitely thin conducting wire. Let's graph that B field. So here we go. B is a function of r. And a nice transition point is going to be the radius of that conductor. It's proportional between 0 and big R. And after that, then it looks like a regular conductor, a thin conducting wire. So in the first part, there it is, just a basic formula for little r less than big R. Then at this radius r, you put in big R for little r, and it just looks like the regular formula for a conductor, followed by an inverse relationship given by that. All right, next thing to look at is the magnetic field inside a solenoid. A solenoid is just a bunch of loops of wire over a spatial extent as shown here. So this is going to be idealized. So in the idealized solenoid, there's you could say an unlimited number of turns. But of course, in reality, there's always a finite number of turns. So let's slice this thing lengthwise, with a samurai sword of some sort. And it'd have to be quite the samurai sword. You'd have to go through it pretty quickly. It'd have to be very tough metal. Anyway, we slice it lengthwise. And so we have the currents going in and the currents going out. Each loop is the same. Now, put your fingers in this side and let them wrap around to the other side. If you do that with your right hand, which way does your thumb point? That's right, this way. So that's the direction of the magnetic field that's produced. Now, what is the size of that magnetic field? That's the question. We're going to choose a special line integral, a special integration path, A, B, C, D, A. Basically, we're going to integrate around the whole path, length L, and see what the integral gives us. Closed integral of b dot dl is BL. We're going from A to B. B is in the same direction as the integration path, so it's just B times L, right? This is length L. So BL. Now as we go from B to C, oops, nothing in the dot product. Out here, there's no B. This is idealized. And D to A, we're perpendicular again, no dot product. So 0 plus 0 plus 0. So we have BL, which is mu 0 I enclosed. Now, mu 0 I, the I that we're talking about here, is in each one of the turns. So we have to multiply it by n turns. And that's big N. So let's do that. So BL equals mu 0, oops, NL, little nl. What do I mean by that? Now don't panic. This is really pretty simple. Little n is simply number of turns per length. So big N is little n, the turns per length, because that's more general, multiplied by the length. Turns per length times length is turns. So that gives us how many turns it is. And so we have our final result. B is equal to mu 0 little n times I. All right, so that is the formula for a solenoid. Mu 0 turns per length times I, because it's an important factor here, this number of turns per length, the density of the coils, so to speak. So B is equal to mu 0 Ni. B equals mu Ni. Boony. Boony. Hey, boony. Boony. Hey, how about this? Bunny. Bunny. All right, you can remember bunny or boony. All right, before I go crazy here and drive you crazy, let me show you just a little graphic. I kind of like this because one concern you might have is, here's the B field coming through. Well, where does it go? I thought they're in loops. Yes, they are. They loop around. In the idealized situation, which I may not very effectively convince you of in this graphic up here, notice the density of the magnetic field inside. And as it loops around, most of the loops are going to be way outside. So basically the magnetic field rapidly trails off out here. And if we do the integration path close in, we got this magnetic field inside and outside. Ideally, we're not traversing a magnetic field along the integration path, even when we're going in the opposite direction that we did inside. So hopefully that makes sense. That is a solenoid. And now on to the toroid. So basically the toroid is just taking a solenoid and wrapping it around into a continuous circle. Kind of has a different feel to it because it doesn't have any ends where the magnetic field can burst forth. And that's pretty key here, in fact. So here it is, a cross section. Let's slice through it. The whole toroid has radius little r, and you notice that I got the current going in here, and it circulates around, all the way around and comes out this side. All right. Then you can see that these wires on the inside are all going into the screen, and on the outside they're coming out of the screen. Okay. So we have three different regions. We'll talk about path 1. Inside this thing, path 2 inside the iron base core of the toroid structure, and then outside the whole thing will be path 3. So now if the coils are loose, now think about this, the charge is flowing around here, okay, and as it flows around through the wire, you have charge circulating around this entire toroid, based on the drift velocity of the charges. So you got these charges flowing around. Well, if you have that, use the right hand rule on the charges, you'll find that you have a B field pointing into the screen here, don't you? Well, if the coils are loose, namely separated by a lot, it won't take long for the drift velocity to cause those charges to move around, and so you have a significant charge circulation velocity. based on the circulation of the charges. And based on that, we have a perpendicular B field that's not negligible. It's significant, or can be. And into the page. Again, grab that with your right hand in the direction of charge circulation. Thumb points in. Now, if the coils are tight, then what we got is this is looping back and forth around here, and it doesn't get around the whole structure very quickly. So we have the tight coils. The charge circulation velocity is small in that case. And so the perpendicular B field, negligible. It's a little jigger. So let's consider path 1. Closed integral of B dot dl, mu 0 I enclosed. How much I is enclosed? That's right, 0. So B1 is 0. Okay, good. Path 3. Considering path 3, what current is enclosed there? Well, every current that goes in comes out. You're circulating the whole thing, so it's also 0. No current enclosed. Hope I didn't say charge enclosed a minute ago. I feel like I did. Well, you know to overcome my limitations there. So B3 is 0 as well. That's pretty nice. No magnetic field inside or outside the material. Finally, path 2. Path 2. B is inside the material. In fact, this material is a nice type of material, iron-based, for magnetic field lines to exist. It's parallel to the path, and closed integral of B dot dl is B times 2 pi r, which is mu 0 I enclosed. Are we enclosing? I enclosed. Are we enclosing any current? Well, yes, we are. We're enclosing I times n, number of turns. Big N is number of turns. So we have B is mu 0 ni over 2 pi r. Booney over 2 pi r. But wait a minute. We have a finite definable amount of turns here. Remember, little n is turns per length, but we know what the length is. The length is 2 pi r. So we have n, big N, over 2 pi r. Well, that's nice, because there's n over 2 pi r. So once again, we have Booney! Or bunny. Take your pick. Now, incidentally, not that important, the magnetic field in the center, as a result of this charge circulation velocity, which has something to do with the number of turns. More turns there are, the less velocity we have. So it turns out to be, this ratio turns out to be about pi over n, inversely proportional to number of turns. More turns, less charge circulation velocity, less magnetic field inside.